Okay. So today you guys don't have a quiz, but we are going to cover quite a bit. We're going to cover 3 laws, and then I'll reserve 2 examples for Monday. So when we come back, what I'll do is I'll do the last 2 examples since we're fresh in memory, and I will do an example from your quiz on Monday too. I thought I was going to be out on Monday, but they moved it to Monday after spring break. So I will be here on Monday to help you guys, but I just decided not to change anything and just give you all day to do just a quiz. So on this warm up, you may it talks about you have 250 milliliters at 25, and then it moves to 40 degrees. So it is just talking about volume and temperature. Okay, 2 temperatures. So which law are we using? T1V1 or V1 over T1? Volume and temperature is going to be V1 over T1. So you're just going to plug in V1 over T1 equals V2 over T2. V1 was 250 milliliters. I do not have to convert milliliters to liters because there's no reason. You can keep it as milliliters. But I do have to convert temperature by adding 273. So you should get 298.5. And then you're looking for V2. And if you add 273 to the 40, you should get 313.5. Okay, so all I've done is I've plugged in into my Charles equation because Charles always has to pee, so he has constant pressure. And when I solve for this, I would do 250 times 313.5 and divide by 298.5. The equations we're doing today are going to be very similar to solving this. So it's very important you know how to cross multiply and divide, which we've been doing since the beginning of the semester. When you do this, you should get 236 milliliters. So if you guys did that and you checked your work, then you should be doing you should feel very confident moving forward. So let's go into our next gas law. So like I said, we'll cover 3 today, none on Monday, 2 on Tuesday, and then you have Wednesday, Thursday to review, and you'll take your test on Friday. So Lussac is the next one. He's a French chemist who he investigated pressure and temperature. So he kept volume the same, but he wanted to see what happened to the pressure and the temperature. So let's think back to our tire, and we go ahead and we keep the same, or we have a pressure, right? We overinflated our tire, but we were like, yeah, whatever. We start driving on it. It's a hot day in Texas, so the asphalt is like 140 degrees, 150 degrees. The air molecules inside the tire start moving faster. What's going to happen to the pressure? Is it going to increase or decrease? Increase, right? They're moving faster. The faster they move, the more collisions on the wall of the container, and eventually your tire is going to pop because it's not going to be able to hold it. So very important that you guys look and see. If you don't know, you can open up your car door, and there's usually a sticker right there that says how many PSIs you should have, pounds per square inch, in your tire, and that's like your running estimate. Every tire is a little bit different. Like if you have low pros, you need to be running a lot more. If you have big tires, obviously you have a lot more. So Lussac again, pressure and temperature have a direct relationship. That means when one goes up, the other goes up, and you have to use the Kelvin scale. Okay, ignore those notes. Hey, and make sure we're paying attention. All we're doing, guys, is notes. I don't think y'all have anything yet. Yeah, nothing yet. Oh no, yes. Using the Kelvin scale. So on Gay-Lussac's law, we're on Gay-Lussac's. So volume is constant, and we have to use the Kelvin scale. And how do we convert to Kelvin? We added. Very good. Thank you. Okay. So you should put when volume is constant. And this only applies when using the Kelvin scale. If I said, put this in degrees Celsius.
Oh, so it's adding Celsius.
Add 273. Yeah, and you should always, yesterday, some people were adding 273 at the end of the answer. That's not what you do. You should be adding 273 before you start the problem. Okay? So Gay-Lussac's law is that P1 over T1 equals P2 over T2. So again, like I said, in the warm-up, cross multiply and divide is very important. So since we've done very similar ones, and we're kind of covering a lot, I'm just going to cover one example. If you guys need me to cover another one, I have examples that I can do individually. But I feel like if you can do one of these, probably do a lot. So I'm going to skip this guy. All right, so it says a gas at 121 kilopascals and 14 degrees Celsius is expanded to 200 kPa. What is the new temperature? So let's write our variables. kPa is pressure. Remember, pressure is in kPas, mmHgs, or millimeters mercury. Our temperature is 14, but we always add 273. So we get 287 kelvins. Our P2, the second pressure we see, is 200. What is the new temperature? Okay. What you want to check is to make sure your pressures are the same. Okay, you guys, to be honest, you guys are academic. I'm not going to throw another wrench into the pile for y'all, okay? So I will pretty much always give you the same pressure. We're solving for K. What was your question, Laura? Sorry. Yeah, your question?
Oh, my question. I forgot the formula.
So P1, which is, so it's P1 over T1.
121 over
287 equals P2, which was 200, over T2.
And then what you do, so you just cross multiply. Okay, right. So you multiply the pressure 2 and temperature 1, and then divide by pressure 1.
Correct.
Would you be able to get just a T-chart? Or would you have to
You kind of just, yeah. So on this, when you guys solve for it, you get your temperature of 474.
Good job.
You do not have to put it in Celsius unless I said, what is the temperature in Celsius? And that's something like I'd put it in red to see if you just read your question correctly. And so that would be something you might see. But if not, then you just leave it as Kelvin. And you notice that the pressure increased and then the temperature increased as well. So not by quite double like the pressure, but pretty okay. Everybody okay on getting this out? Yeah. All right, so let's do combined gas law. So the name is combined gas law. What do you think we're going to do?
Combine.
Yes, that is exactly right. So let's review the ones that we have so far. This one has pressure and volume. Which law was that? Boyle's, Charles, or Gay-Lussac? Pressure and volume. Same temperature, and who always is at the same temperature? Boils, right? Water boils at the same temperature. Okay, here we have pressure and temperature changing, but volume remains the same.
No,
Gay-Lussac. Okay, so I've had some people come up with some crazy things for how to remember volume is the same, but they're not politically correct, so I can't say them. But come up with your own. So the combined gas law is P1 times V1 over T1. I don't like it. It's not hard. Equals P2 times V2 over T2. So yes, there are 6 variables, but don't let that intimidate you because it is the same setup as Gay-Lussac and Charles's law. Just 2 more variables. Okay, but you'll solve it the same way. You're still going to cross multiply and divide, except this time you're going to divide how many times? 2. Yep, very good, Brianna. Twice. Okay, so again, pressure, just make sure your units are the same. Y'all are academic, I'm not going to do that to you. Make sure your volume units are the same. I'm not going to do that to you. And then their temperature has to be in Kelvin. So that's the only things you're going to need to check. So I'm going to skip an example and go straight into the one you guys have. A 1.5 liter, what is that? Pressure, volume, or temperature?
That is volume.
Very good. Volume is 1.5 liters. These aren't hard. What's hard is that people don't know how to identify the variables. Okay? A sample of gas at 5 degrees Celsius is a what? Temperature. Very good. 583 mmHgs.
That is the pressure.
There it is. Make sure y'all know what all these variables, if you want me to, I need to write them down, I will definitely go through that. Then it says new container is now at 10.5, so that's a new temperature. We always add 273 to Celsius. The pressure is 615. And the new volume is our unknown. Okay, so yes, lots of variables. Don't let them scare you and be like, math, that's it, I'm done. I hate you, Mrs. Cruz. Okay, don't hate me. I didn't make this stuff up. I just... Okay. So let's just plug into our equation letter by letter. So P1 is 583. And just check your units. I mean, everything's going to check out. I'm not going to do that to y'all. So pressure is 583. Volume was 1.5. And our first initial temperature was 278. Our second pressure was 615. Our second volume is what we're solving for. And our second temperature was 283.5. Okay, so we also get to fill that in. It's not hard, I promise. I'm gonna show you. It's not hard. It's a lot. That's why there's only like one of these on your quiz on Monday. I think one, maybe two. And then your test, depending on which version you get, you'll have one. Okay. So when you solve these, it's still cross multiply and divide. You're going to multiply the side that you have everything in. So 583 times 1.5 times 283.5. Press enter. Then divide by 278. And divide again by 615. So you're dividing twice. So if you do this correctly, you should get 1.45 liters. Yep. So to solve this, 583 times 1.5 times 283. Enter, just so you don't make mistakes. 278 divided by 615.
Equals divided by.
So if y'all just take it step by step by step. The thing about math is you really can't go faster.
Oh, so we divide by, okay.
You divide twice.
1.44.
Yes, very good. I think it's like 1.48 or 1.47.
Yeah, 1.447.
Pretty good memory. I did it like 2 weeks ago. So pretty good.
It's 1.4500.
Yeah.
One.
Depending on how, yes. All right. Let's do one more example of combined.
There's about 278. Who's that? Who's that?
Okay. An 18.2 liter. That is a volume. Is at 95 degrees. And 1 ATM, so ATM is pressure. And it says it's placed in a 15 liter, so that's the second volume we're seeing at 80 degrees Celsius. What is the new pressure? So the way that I know this is combined gas law and not just boils is I have pressure, volume, and temperature all changing. Now, actually, the combined gas law is P1, V1, or N1, T1. But generally, with academic, I'm not going to put another variable in that. Okay, so I'll just keep it as P1, V1 over T1. So let's just plug in our numbers now that we have our variables. We have P1, which is 1, times V1, 18.2, over T1, equals P2 times V2 over T2.
I feel like I do this all the way around. Oh, not
Okay.
Oh.
To solve, I'm going to multiply 1 times 18.2 times 353, enter, divide 368, divide 15. And when I do that, 1.1.
Yeah, I got it. Why did I first get, I don't know why I first got like 0.
I got like 0.21 because I forgot you had to add a 273 to the 8, and I was like, what?
That's never forget that. And I wish that I could just like give y'all Kelvin every time and hopefully the same, but
Oh, you're right.
I'm keeping it realistic. Okay? So let's do ideal gas law. We're just going to introduce a law, do one example, and then we'll be done so you guys can finish Charles and Boyle's, rest your mind, whatever else you need to do on Friday. Yes.
For this one, I got 1.16.
So technically 1.2, yeah. But remember, I'm just throwing like sig figs and rounding out the door. And as long as you guys are like in a range, and I usually go from whole number to whole number. So like, for example, this one I would say, if you answered anywhere from 1 to 2, then your answer would be right.
Okay.
I'm trying to keep it good for y'all. Okay, so let's do ideal gas law, which is the other sheet. And then we are done. So we'll have a good 35 minutes in this class.
Plus the budget.
Plus the budget.
Why? I have to go to industry and house.
Okay. So the ideal gas law is not going to be changing different variables. It's going to be seeing how those variables affect an ideal gas. So the ideal gas law is PV equals NRT. And I'll talk about what all those variables are, which we already know what pressure and volume are. N is the number of moles. Don't let that scare you. It's just going to be like, here's 4.3 moles. R is a gas constant. It does have 3 values. However, those will always be given to you. And then T is the temperature. So
It is the what?
N is the number of moles. I think it's on the next page, which I'll need for your notes. So P is pressure. Remember, pressure can be ATMs, mmHgs, or kPas. So it can be any of those 3 in these equations. V has to be in liters. So volume in units of L. N has to be in moles. And the R has 3 values. So the 3 values could be 0.0821 liters per ATM, or you could use 8.31 liters per kPa, or you can use 62.4 liters per mmHg. What was the difference between all 3 of those?
I don't know.
Different numbers.
The decimals are, I don't know.
What about the units? What about the units? What was different about the units?
mmHg, kPa.
Very good. So the pressure. So depending on which pressure you use in your equation determines which R you will use. And I will do an example of that.
Is this one the hardest one?
Usually combined gas is the hardest. Not hard. Once I work through one, y'all are good. So you fill a rigid steel container that has a volume of 20. It has 4 moles. Remember, that's your N. Temperature is 31. Well, we add 273. What would be the pressure? And it wants it specifically in kPas. So let's determine which gas law we're using.
The last one.
The last one, right? Obviously. But because there's only one P, one V, one N, and what else do we need in here? R. Which R will I use considering we've asked for kPa? So
We
pressure.
will use 8.31
Very good. Does everybody know why?
Because that is what it says, that's the number for K.
That's yes. So you have to use it to cancel them out, right? So 8.31, and I'll just write out the whole unit so y'all can see why. Liters per kPa over mole K. It's a lot of units for one number, right? So liters we canceled out with our volume. Moles we canceled out. K, check our answer label. We cancel out, and we'd be left with kPa's, which is what we want. So let's plug into our equation. P is our unknown times V, which is 20, equals N times R times T. How do I get little p by itself? Divide by 20. Right, we divide by 20 on both sides. When we do this, we're multiplying 4 times 8.31 times 304. We should get 505 kPa's. If this were a normal year, guys, and we were doing like traditional paper testing, I usually take off 2 points for not identifying your final answer, 2 points for no unit, and 2 points for sig. Thankfully, this is not. Okay. The valedictorian of Northbrook High School, the only non-100 he ever made was in chemistry, and the only reason he didn't make 100 in chemistry was because of sig figs. But he emailed me 2 years later and said, I dominated sig figs in college chemistry because of you. So he's like, even though he hated me when he was in college, high school, his only non-100. So, all right, that is going to be. We have 2 more gas laws we're going to cover that are super, super easy on Tuesday, but that's pretty much the harder of the gas laws. So let me check in with virtual learners, and then